You know that feeling when your phone lags or your computer freezes for a second? It's annoying, right? But what if that same delay happened in your car's airbag system? Or a surgical robot? Well, in some systems, a millisecond of lag isn't just an inconvenience, it's a catastrophe. Today, we're going to dive into the special class of operating systems built for exactly those moments, where timing isn't just a feature, it's the entire point.
It sounds like the start of a weird joke, doesn't it? I mean, on one hand, you have a life-saving safety device. On the other, a high-precision weapon. They exist in completely different worlds, but believe it or not, they share a single, fundamental, non-negotiable requirement.
And the answer is timing. It's all about timing. Both of these systems absolutely depend on an operating system that guarantees an action will happen within a super precise window of time, every single time, without fail. So, welcome to the world of real-time operating systems, or RTOS for short. So, how in the world do these systems pull this off? Well, here's how we're going to break it down. We'll start by defining what an RTOS actually is. Then we'll look at its core features. After that, we'll explore the different types, because it turns out not all deadlines are created equal. And finally, we'll see why this unseen OS is so critical in the technology all around us. Okay, first things first. What exactly are we talking about here? This is more than just a fast operating system. The real definition, it's all about guarantees. Let's start with the official, technical definition. The key phrase to grab onto here is bounded response time. All that means is there's a hard, predictable upper limit on how long a task will ever take. It's not about being instantly fast. It's about being predictably fast. Here's a simpler way to think about it. See that word intended? These systems are purpose-built. Your laptop's OS is a jack of all trades, trying to juggle web browsing, email, and your music player all at once. An RTOS? Nope. It's designed from the ground up for one mission, to serve specific, time-sensitive tasks. And this definition, this one really gets to the heart of how it all works. It's all about interrupts, signals that demand immediate attention. An RTOS doesn't just try to handle them quickly, it promises to handle them within a specified time, no matter what else is going on. And that is the core difference. It's not about raw speed, it's about that rock-solid guarantee. So how does an RTOS actually make these kinds of guarantees? It's not magic, it's a very specific set of features that makes it totally different from the OS on your phone or computer. An RTOS has a few key tricks up its sleeve. It's got to be able to prioritize tasks, let them talk to each other, and do it all with minimal delay. But the one feature that truly makes it all work, the secret sauce, is a special kind of multitasking called preemptibility. Just look at the contrast here. In a normal system, if some low-priority task starts, say updating an icon on the screen, it usually has to finish what it's doing. But in a preemptive RTOS, if a critical event happens, like a sensor detecting a car crash, the OS can immediately interrupt or preempt that icon update to fire the airbag. That ability to drop everything for the most important job is what makes this whole thing possible. And that brings us to latency, basically a time delay. Every system has it. But in an RTOS, the time it takes to switch from one task to another isn't just tiny, it's consistent. It's known ahead of time. In this world, predictability is king. Okay, so we know an RTOS has to meet deadlines, but it turns out not all deadlines carry the same weight. And this leads to a whole spectrum of what real time can mean. See, the type of RTOS isn't defined by its speed, but by something much more dramatic: the consequences of being late. What happens if it misses a deadline? The outcome can range from a tiny glitch to, well, total system failure. Let's start at the most critical end of that spectrum, the hard real-time system. Here, the word deadline is meant in the most literal sense possible. Missing it means the system has failed. Completely. There is zero, and I mean zero, tolerance for being late. And this brings us right back to our opening question. A missile that corrects its course a split second too late? It misses the target. An airbag that deploys a fraction of a second too late? It's basically useless. These are the classic examples of hard RTOS, where the consequences of being late are as severe as it gets. This is the bottom line. It's a simple binary outcome. You either meet the deadline and the system works, or you miss it and the system fails. There is no in between. All right, moving on, we get to the middle ground, firm real-time systems. In this case, a missed deadline is really bad, but it's not catastrophic.
what happens is that any work done on that late task becomes totally useless, and that leads to a serious drop in the system's quality or performance.
A perfect example is a robot on a car assembly line. If it misses the deadline to put a weld on a car frame, that specific weld is just missed. The whole factory doesn't explode, but the quality of that one car is now shot. The result of the missed task has zero value. So for a firm RTOS, the system itself doesn't crash and burn, but missing those deadlines makes it do its job so poorly that it might as well have. And finally, we have soft real-time systems, which are by far the most common ones we interact with every day. In a soft system, the goal is still to meet the deadline, but if it's missed, the result is still useful, just a little degraded. Think about it like this. When you're streaming a video and it buffers for a second, a few frames have just arrived late. It's annoying, for sure, but the video doesn't crash, you just get a little stutter. That late data still has value once it finally shows up. The same thing goes for a little bit of lag in a computer game or the time it takes to process a photo on your phone. And this really nails the key difference. A soft RTOS is all about best effort. It tries its best to hit every deadline, but the world doesn't end if it misses one every now and then. Being on time is the goal, but it's not an absolute life or death requirement. So we've defined what an RTOS is, we've seen how it works, and we've walked through the different types. But let's bring it all home. Why does any of this matter? Because these operating systems are literally everywhere, working silently in the background of our lives. They're in the anti-lock braking system that keeps your car from skidding, they're in the pacemaker that keeps a heart beating correctly, and they're in the flight controls of every modern airplane. They are the unsung heroes making sure our most critical systems are not just fast, but predictably, reliably on time. And that kind of leaves us with a final thought to chew on. As we move towards things like self-driving cars, remote robotic surgery, and fully automated power grids, the number of systems where failure is not an option is just going to keep growing. So the question is, what's the next big challenge that will demand the absolute precision of a real-time operating system? What's next on that list of things that simply cannot be late?